Now we are moving to 15.3, which is area by double integration. So far in 15.1 and 15.2 we have used double integration for finding volumes over general regions or rectangular regions. So it has been used for finding volume. But here in 15.3 we are using double integration for finding area. As you have studied previously, we were finding area using what? Using single integration of if we had two functions, we were saying f minus g dx where f was greater than g. Or if we were finding the area between a function and the x-axis, we were saying simply the one single integration of f dx. But here, when we are finding area between two functions, we are using double integration. How do we use that? Here, the area, the definition is here, can be found by a that's equal to double integral over the specified region dA. That dA, as you know, represents either dx dy or dy dx, and you're free to choose whichever you want to find, whichever you want to evaluate. Let's move to the first example and see how is this rule of double integral works for finding the area between two curves. From example 1, it's required from us to find the area of a region that's bounded by y equal to x and y equal to x squared. So here, of course, since it doesn't say double integration, you can simply use the rule that you have studied previously for single integration. But here, since our subject is double integration, so we are using double integration for finding the area between those two curves. I'm moving to see how to sketch again this region. As you know, we again have got x-axis and y-axis. Y equal to x squared, the graph of it is like that, and y equal to x, the graph of it is a straight line. Sorry, it doesn't appear to be very straight. So we are having this as the area between the two curves that we want to find. On the left side, I have drawn the graph in a better way. Okay, so we are studying on that graph to find the intersection points, the areas, and how to do the double integration, how to evaluate the double integration. Okay, so as you know, we have got points to find. Every time when we are dealing with double integration, or even with single integration, it's really important to find the it's really important to find the specific points. Here, this one is origin, okay, and this point, as we know, we can find it by simply equalizing the two functions to each other, since this is the intersection point of those two functions. So equalizing them to each other, x squared equal to x, of course, rearranging it, x squared minus x is equal to 0, taking a common factor. So here x is equal to 0 or x is equal to 1. We already know that those two functions are intersecting at 0, but here what is required from us, what we want to find is this point, which is 1. Here is also 1, and the y coordinate is also 1, because inputting x into this one gives me y equal to 1. So this is what we have got as a graph, and we want to find the area that is between those two curves. To do so, we have to do what? Double integration. Our subject, since it's double integration, so we're finding the area using double integration. Either you're using double integration by dy dx or dx dy, it doesn't matter. But we have got one thing here, as you see from the rule, there is nothing inside the integration, okay? Inside the integration is empty. There is only one constant number 1 in here. so it is only the double integration and the dx dy or dy dx in it. So here we have got this one. Let's first do dy by dx. When we are doing dy by dx, what do we have to do? We have to draw a vertical line, okay, from here to there. It is entering the region that we have got from x squared. So here the bound of this one is y equal to x squared, and it is leaving the region in the function y, from the function y equal to x. Y equal to x squared. Okay. For considering the x boundaries, we know that the region that we have got runs from 0 to 1. So here the x that we have got is 0, and the upper limit of x is equal to 1. Now we want to solve this integral. It gives us what? With respect to y, it gives us integral x from 0 to 1. As you know, we are not solving this one first. Gives me y with respect to y, where it runs from x squared to x, and then we have got dx. Solving this one simply, we get what? We get x from 0 to 1. Here when we put instead of y the x's, so it gives me x minus x squared dx, which is a very simple integration, giving me x squared over 2 minus x to the power of 3 over 3, and the integration runs from 0 to 1 and gives me the result 1 over 6. Okay, so this is the the application of double integration for finding the area between two curves. If you look at here, okay, just as a note, this is a single integration. This single integration that we have got, it is from 0 to 1 f minus g dx, where f is the greater function, which is x, and g is the smaller function, which is x squared. So using double integration still gives us what? In the middle of its solving, it gives us the single integration that we have studied previously for finding the area between two curves. So this is what? This is the way of finding area using dy dx. Okay, how about if the order of integration is dx dy? Of course, the idea is the same. Okay, I'm solving it here just to see how we deal with it. So the integration becomes what? Here we will have dx dy. For doing this one, we have to draw a horizontal line. Okay, so drawing a horizontal line through the region, it is entering the region in that point. So the function x is equal to y, and leaving the region through the function y equal to x squared, writing it in terms of x equal to something that's x equal to square root of y. We are taking only the positive side of this square root because we are working in the first quadrant. Now we are moving to the values of y. Okay, we found the limits of x, now finding the limit of y. If you see the area that we have got, it runs from 0 to 1. So the limits of integration for y becomes y equal to 0 and y equal to 1. Solve that integral. We get what? Y equal to 0, y equal to 1. With respect to x, I will have x running from y to square root of y, and we have got dy here. Simplifying this one further, or let me say substituting the limits of integration, gives me y equal to 0, y equal to 1, and this part becomes square root of y minus y, okay, dy. Taking that integration, evaluating that integration again must give us some other steps, and then the result again will be 1 over 6. So that is how we are using double integration for finding the area between two curves. That's all about example 1. We are moving to example 2. Example 2 states that we have to find the region, the area of the region that's enclosed by the parabola, that's y equal to x squared, and the line y equal to x plus 2. Let's see how can we use double integration for finding this area between those two curves. Again, here we have got the example y equal to x squared and y equal to x plus 2. Let's draw it here to see how the steps are done, and then we are doing the other steps on the sketching that I've already done. Y equal to x squared, it is obvious that the graph of y equal to x squared is like that, and y equal to x plus 2, it's x moved up 2 points, so it gives me something like that. Okay, so this is the area that we have got, and we want to find using double integration. I'm erasing the extra parts so that we will not have a lot of mess around. So we are having the shape that I have already given to you here. Okay, this one. We are trying to find this area that we have sketched here. Okay, the key things, as usual, that we have to find is what? To find the points. The points are the key things later on for finding the, what's it called, the limits of the integration. First, to find the limits of integration, I'm using the order of integration as dy dx. When it is dy dx, what do we have to do? We have to draw, or let me say, first we have to find the points, then we are drawing the vertical line through the region. Okay, for finding the points that we want to find, here is of course 0. That is pretty much obvious. I have to find this point and that point. Okay, what are those points? Again, those points are the intersection of the two functions, so we can simply find them by equalizing the two functions to each other. So here I get x squared is equal to x plus 2. Reordering the equation, minus x minus 2 gives me 0. So here x minus 2, x minus 1 is equal to 0. So x is equal to 2, or x is equal to 1. Okay, sorry, here this one is plus 1. Okay, when we multiply them we get minus 2, and when we add the two of them we get the middle term, so this one is minus 1. Okay, so that point here we have got, here is minus 1. Okay, and here this point is 2 on the x-axis. So this point is minus 1. Putting it in one of the equations, for example this one, minus 1 plus 2 gives me 1, so this point is 1. Okay, and if we have got y is equal to 2, so it becomes 2 plus 2, y is equal to 2 plus 2, that's giving me 4. So this point is 2 and 4. Now we found the points that we always need in finding the limits of integration. Now we are coming to deal with limits of y, then limits of x. If we have got the order of integration is dy dx, so again we have to draw a vertical line. Wherever we are drawing the vertical line, it's still entering in the function. That's what? Equal to x squared. And leaving at the function y equal to x plus 2. Okay, if you're drawing the vertical line here or here, anywhere else, it's still living in the same place. Okay, so we have got one piece of integration. Okay, now for limits of x, if you see when this area that we have got, it's running from -1 to 2. So x, the limits of integration is from -1 to 2. Now solve this integration as we have done usually. This gives me what? Integration from -1 to 2. And with respect to y, this gives me y with the limits x squared and x plus 2 dx. Substituting those limits and then finding again integration with respect to x will give us the result of this area, and the result is given as 9/2. Okay, I'm leaving these steps for you because these integrations are pretty much easy for you to evaluate. That's why I'm leaving them. Okay, so this is if you have got the order of integration is dy by dx. How about if you have got the order of integration as dx dy? So we want to find the area between those two curves using the order of integration as dx dy. Of course, when we want to use the order of integration as dx dy, we have to draw horizontal lines through the region that we have got. First, I'm drawing the horizontal line from here to there, going through the region. When you see the entering place is here, okay, here, and the leaving place is here. But as we said, when we are drawing horizontal or vertical lines, that horizontal line must enter and leave in the same place. But when we see that region, when we are drawing another horizontal line somewhere else, for example here, okay, it is entering this function here and leaving it in that place. So we will have two different regions. The first region is still from the bottom to the yellow line that we have got, and the second region starts from the yellow line to the top of the graph that we have got. So considering the first region, you see that the entering place is what? Is the function y equal to x squared. So writing it in terms of x equal to something, here we know that y is equal to x squared. So x is equal to what? X is equal to positive or negative square root of y. Since we are on the left side of the y-axis, we are choosing the negative square root of y. Okay, where does it get out? Where does it leave the function? In that point. That point is what? X is equal to positive square root of y. So the upper limit here becomes positive square root of y. How about the y limits? The y limits for region 1, it starts from here, okay, and ends here. So it starts from y equal to 0 to y equal to 1. So that's the first region. Okay, here this is the integral over r1, and this one is the integral over r2. Now moving to r2, let's see how the limits of integration change. Here the entering place is this one. Okay, here x is equal to what? X is equal to y minus 2, because we know that this is the line y equal to x plus 2. So x is equal to y minus 2. Let me write this one better. And where does it leave? It leaves the region in that point. What is that point? It is the function y equal to x squared, and x here is equal to square root of y, as we have mentioned it previously. So this is square root of y. Now we are coming to the limits of y for region 2. For region 2, I'm moving this one here, and this is the point 4. For region 2, where does it start and where does it end? Region 2 starts from here, okay, and ends here. So it's starting at 1 and ends at 4. And this is the way of finding area between two curves using the order of integration as dx dy, which gives us two regions to be calculated for finding the area of the singular region that's required from us. Of course, again, you're solving these integrations with respect to x, putting the limits of x, and then with respect to y, putting the limits of y, and giving us the result equal to 9 over 2 at the end. Again, I'm leaving the integration, solving the integration for you, since these ones, as I've told you, are very easy calculations of integration. We have got one thing left for section 3 of chapter 15, and that is average value. What is the average value? We have got a rule here. Average value of f over r, it's equal to 1 over the area of the region, okay, multiplied with the area of the region, okay, which is the double integration. Here we have got example 3. It says find the average value of f of xy, that's x cosine xy over the rectangular region, this one. This rectangular region, we have got a rectangle like that, okay, starting from 0 to pi for x-axis, and for y starting from 0 to 1. So what is the area of this rectangle? Area is equal to length multiplied to width. Here is pi, and here is 1. So area is pi multiplied to 1, that's equal to pi. And you're finding the double integral of this function, which gives you the value 2. So the area, the average area becomes what? Becomes 2 over pi y, because it is the double integral over the area of r. Area of r, we found it, that is equal to pi, and this double integral, we found it, that's equal to 2. So this average value of f is equal to 2 over 5. That's all about 15.3, which was the application of double integration for finding the area between two curves. Have a great time.